How's it going? Trey Clark here, and I'm going to jump right into this as I usually do. All right, we're going to talk about the inverse squared law. Why are we talking about that? Because I'm a physicist? No, I'm not. And I get reminded that every time I use the same math that physicists use, and they say, don't do that because you don't have those names that you went into life debt for in college. I'm a photographer, okay? This happens to be a P900, which is relevant here. But when you figure out, I'm not going to get into the details of photography, but you have to use the inverse squared law to figure out your lighting, your f-stops, basically. And how you're going to get a picture, the beautiful pictures that sit on coffee tables around the world, especially recently with the moon landing's 50th anniversary. So how did they get these pictures? What beautiful camera that I would be hard pressed to take as a very experienced photographer. They could probably teach classes on the inverse squared law and everything from aperture to shutter speed, how you tie them all together, your ISO settings with a DSLR camera that almost teaches you them with their programmed auto settings. You can almost work backward just by looking at the readings and making note of stuff. So not to get too much into photography, but it is important that I'm no dummy when it comes to photography. So depth of field, shutter speed, light, all those things I can do in my head manually, and I've made myself do it. So it's actually how I learned. So you have what's called lumen and lux. We're talking about the moon. So tonight, to put it in perspective, the moon is pretty dang bright. It's not quite harvest moon bright, but it's casting shadows. You could easily walk around the streets with no lights at all. And just to put it into perspective, it's about there. So with the readings from my camera, it's looking at about a 0.7 lux. Now lux is basically a lumen per square meter. If you've ever bought high-powered flashlights, this candlelight stuff, don't worry about the conversion of it. We're starting with, I'm going to dumb it down to 0.5, which is definitely lower than what it is, but also for math's sake. So when you look at a bright moon, just picture 0.5 lumen, and we'll get out of the decimals pretty quickly here. So the moon is about 240,000 miles away, give or take a couple thousand miles. So the inverse squared law dictates, because it's a law, it's not an opinion or something that changes depending on your day of the week or whatever. It's a law. The difference between a theory and a law is that it cannot be disproven by anyone. It never has been. It is a law. The inverse squared law means that your distance towards or away from a light can be cut or multiplied by, okay, let me start backwards. If I am this far away from this light that you can't see, if I'm 10 feet away, if I cut the distance away from the light in half, the light will appear to whatever meter I'm using. I'm not even talking about my eyes or whatever. It will appear to be, it will register 4 times the intensity that it did before. It will trigger everything on this camera to make it 4 times as bright. If I go from 10 feet to 5 feet. Now, the reason I'm making this point is that if you're a physicist or an engineer or a photographer or whatever, this is a law that you're going to have to put your reputation on the line to tell me where I'm wrong. I still might be. Fair enough. So we're going to see what this looks like. From 240,000 miles is you're an astronaut closing in on the moon in brightness. Now, why is this important? Because we need to have really good visors and window shields? No, it's because now I have the specs, and I have had them, and this is what bothered me all along. I knew we used the Hasselblad camera, and I knew it was a 500 model of some sort, but I never really cared that much about film once I really got into DSLR. The Hasselblad that they use is a chest-mounted camera. This is very important. It's right here. What else is even more important is that they did not use this without mittens on, in a vacuum. Basically, almost impossible to, it's like putting flippers on your hand. There's no way you can do any, I couldn't operate this with mittens. And this is, I mean, I know where everything is on this camera right here. There's no way I could get a good picture. And not only that, because you're wearing a helmet that doesn't move and you can't look down because there's something right here in your helmet in your way. Even if you did, there's no viewfinder. There's nothing right here. There's no viewfinder on the whole camera. Everything is done manually. So before you even take your picture, you have to take your fumbling, mitten-ridden hands and start doing this kind of stuff to set your aperture, your shutter speed, everything manually. It's the 500E or EL, but it's all, that stands for electric. But the electric part, and I've looked all this stuff up, and you don't have to look very far online. The only electrical part or motorized part was to wind the film, and also after you pull the trigger to take a picture, to move on to the next frame with the film. That, just a little side note, had to travel through radiation twice, Van Allen belts, and if you made the mistake of putting it through an airport X-ray machine, you would lose all of your film, and it happened to people all the time. So, whatever. Let's just take that off the table. We'll give you that. Just for whatever reason, as the astronaut said, I can't remember which one it was, but he said, when he was asked by a reporter, what about the Van Allen radiation belts? And he said, well, I mean, you can find this, I just didn't pull it up. We didn't have to worry about them. We didn't know they were there. Okay, fair enough. And then we lost the telemetry data. Let's get back to why the inverse squared law is probably the most smokingest gun there is. And I will start with this. We're going to use 240,000 miles away, even though it's 239 and change, for decimal's sake. At a 0.5 lumen, which is being very, very forgiving for what my reading was tonight. It's a very bright moon. So, and also keep in mind that once you get out of the Earth's atmosphere, you should actually reset your perspective of this whole phenomenon, because then you are suddenly nothing but a vacuum between you and there. So this is actually forgiving in more ways that I can even add up. So we are at 0.5 lumen, lux, lumen per square meter, I think is right. But just call it 0.5 is your perspective of a very bright moon at 3/4 shape. Okay, that's all you need to know. So every time I say it is now this number of lumen, just think it's that much times brighter than what you're looking at right now. So what you do is you cut the distance in half, and then you multiply the brightness to your perspective. We're not talking about your eyes, we're talking about a meter, a measurable meter that can do it very accurately, way more accurately than they could do it back then. And also before we ever went to the moon to even test if we're even right about how far it is. Okay, put all that on the side. So 0.5 lumen, after cutting 240,000 miles in half, is now 120,000 miles away. 0.5 times 4, inversely squared, is now 2. Okay? Now we're going to do that again. 2, no big deal. It's just twice the exposure. Keep in mind also the Hasselblad has a 5.6 f-stop. This is a very earthly f-stop using very earthly film on a very earthly camera. So if you get astronomical with stuff and you didn't ever test it, to get coffee book style pictures is a miracle, especially if you can take them at like 1 every 9 seconds, and that's not even true. So the second time you cut it in half, 110,000 times 4. It's cut in half, inversely squared. So now you got 8 times the brightness that you see with your eyes or with your camera. So then do it again, 55,000 times 4. You're 8 times 4. Now you're at 32, right? Still, you're not in crazy world with it. Then it starts getting interesting. Then you cut 55,000 in half, 27,500, and then you're at 128 times what you and I see as far as brightness. This is a law. This is not my opinion. This is a law that you can use universally with any situation that has to do with knowing how bright something's going to be compared to your distance to or from it. So then, and I'm going to run through this real fast until it gets kind of crazy. And then you cut 27,500 in half, 13,750 in half. Now you're 512 times as bright as what you would notice it normally with any instrument or your eyes. Then you cut that in half, 6,875 miles. Now you're 2,048 times the brightness. Now it's getting at least interesting, but probably something that we could foresee and figure out. So then so now you're almost 7,000 miles away, 6,800 miles away. Cut that in half, and now you are 3,437, 500 miles away. No, 0.5 miles away. So now you're at 8,192 times your perception of its original glow, its original brightness. Now we're getting a little interesting. Cut that 3,000 number in half. Now we're at 1,718.75, and now you're at 32,768 times the brightness. Now we're really having to have predicted from Earth with an earthly camera, with earthly settings, with mittens to set everything, to take perfect pictures, not just good pictures, not even altered pictures, although some were, but without being able to see anything. Preset stuff, you know your distance. If you're 11 feet, it's out of focus. If you're 9 feet, it's out of focus. If your shutter speed is off, it's too dark or whatever. And you have to do all kinds of stuff in a film room, not even stuff that there was no Photoshop back then. So now we're at 32,768 times brighter, right? Then we go to, we're going to cut the 1,700-ish distance down in half, which will multiply the brightness times 4. And I'm going to run through these until I get to the end. 859,375. So just under 1,000 miles away is now 131,072 times as bright as the moon. Still got to use that camera. And you've never done it before, and we're going to get it right the first time. Then 429.69 miles away is the next cut in half, and that times once the inverse squared law is put in. Now the moon needs to be 288 times the brightness that you would register from the Earth, and that's not even counting atmosphere. Then you cut that in half. Now I'm just kind of cutting the decimals out just for math's sake. Call it 215. 215 miles away. The moon is now 2,097,152 times as brighter. Let's keep going. Cut 215 in half, 122.5 miles. Now you are 8,388,698. I think that's right. I've scribbled a little bit. Somewhere in there, times brighter than your perception of it on the moon, whether it's with the camera or your eyes. This is a law. It's not my opinion, and it doesn't matter what the source is or why it got here. It is your original perception as you get closer. There's no argument here. And then, of course, I started running out of decimals. Then we cut 122.5 miles in half. Now we're at 61.25 miles away. Of course, we're traveling in this hunk of junk. It originally, as we started the landing pattern, at 4,000 miles an hour, something like that. Okay, whatever. We'll give him that. Good job, Neil. We're at 61.25 miles away from the surface of the moon. And this is how much brighter the bright moon is tonight to any instrument that we could read. And this is way better than any instrument they had back then. 33,554,432 times brighter than anything we got here as far as being able to detect it. 33,554,432. If you're a physicist, chime in. Tell me where I'm wrong. I don't care who you are. I'm a photographer. You can tell me I'm not a physicist all day long. I know how the inverse squared law works. I didn't even know I knew how it worked. I just kind of had to muscle through it just to kind of go, yeah, okay, cut it in half, multiply it. But I don't even know that I knew the term inverse squared law. I just knew how to figure out my f-stops with the lighting reading. If you're an engineer, chime in. If you are someone that thinks that people that don't have PhDs by their name are too stupid to ask questions, challenge me. This is one you're going to have to really do some mental gymnastics. And if you find yourself going, well, it's still not right, try and look at it through a clear lens, pun intended, and just go, who's trying harder? All I got to do is do this, apply a law that everyone uses, including NASA, including every physicist, including every photographer, including anyone under the sun that is going to get an accurate reading of anything. I'm using the same thing. That's why I say, make everyone play by the same rules and see what gets skewed. Guess what? It's not me, you fucking liars. And I know it. 33,554,432 miles or times brighter once you're on the surface of the earth. You're going to take a picture. I mean, it's got to be creeping up on the surface of the sun. So let's say the surface of the sun is the brightness coming up on you, and you're going to take perfect coffee table pictures with mittens and no viewfinder and you're a layman photographer. You're a pilot. You're a military pilot. So you're so good that you can set everything before you even look through anything, and you set your distance. Fuck you. You're a liar. No. No, 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 no. Do not believe them, and do not let them tell you for one goddamn second that you're not allowed to ask questions. It took me 3 years to figure out something that was sitting right in front of my fucking face. And I'm more mad at myself than I am at NASA right now. But stay with it. Cheers, guys. You have a good one.